Okay, so this is joint work with, So this is joint with Cornelia Wiesmann and Adara Blaga. Okay, so my plan is to introduce this topic and to introduce the definitions and some of the results through one example. Okay, so I will tell you about the spheres on the duals of Lie algebras, and then I will, through the example, I will tell you which results are general, and so you get more familiar to the topic somehow. Okay, so something else that I wanted to say is that this about dual pairs, actually, we are planning with Pedro to study like a more general setting where all these dual pairs, where you can see as an example these contact dual pairs, symplectic dual pairs, these Dirac dual pairs, and so yeah, so this is a plan. Okay. What inspired us to get to this notion of contact dual pairs is this topic about symplectic dual pairs. So let me tell you a little bit about these symplectic dual pairs. Symplectic dual pairs, you can think about them as Morita equivalents between Poisson manifolds, two Poisson manifolds. Okay, so what you have is that you have here two Poisson manifolds, and a symplectic dual pair, it's a symplectic manifold that realizes both of them. Okay? So here you have two maps which are Poisson. And it realizes both of them in a way that the kernel of the fibers, so the fibers are symplectic to each other, symplectic orthogonal to each other is symplectic orthogonal to kernel of T beta. And the other condition is that if you look at the space of functions of these two manifolds inside of sigma, they centralize each other. Okay? So if you look at the pullbacks of, so you do at the pullbacks of functions on P1, and so these two spaces live inside of, they live inside of functions of sigma. What I'm saying is that they centralize each other. Okay? So if you spell out this condition and you assume some things, then you get some more like finite dimensional conditions that are equivalent to this part here. Okay? And these conditions are that, well, actually this is the condition. This is the condition, but then assuming some things, you get that these two are equivalent. Okay. So if you think about these two things at Morita equivalence between these two Poisson manifolds, then of course you should get some results that relates the geometry of these Poisson manifolds. For example, if you assume some things, then you get that you have a correspondence between the space of between the leaf space of both. Between the leaf space. So what you get is that if you take a leaf, a symplectic leaf in this space, then you you can take the inverse image of this leaf, and then you push it with beta. And then you get another symplectic leaf. And this is a correspondence under some assumptions. Okay, so let's see why, like a very natural example that comes from these symplectic dual pairs. For example, if you take a Hamiltonian action on a symplectic manifold, Hamiltonian action, and you consider the moment map, which is a map that goes from M to the dual of the Lie algebra of G. This is Poisson. This is Poisson. Okay, but then you have this natural question, which is, what happened with the quotient? Okay, so you actually have two maps. M, this that goes to G star, and the one going to the quotient, assuming that this is a manifold. Okay, so this map J is Poisson, and this map P, so this quotient, of course, because G preserves the form, then you have a Poisson structure on the quotient. Okay, so how these two geometries are related? And under some assumptions, you can actually, well, this is a dual pair. If you check this condition, this is a dual pair, okay? And one of the consequences is that under some assumptions, you can describe the symplectic leaves of this manifold just at looking at the symplectic leaves of this manifold, G star, and then you take the inverse image and you mod out by the action. And here you already, well, the symplectic leaves of G star are very well understood. They are just the coadjoint orbits of the action of G via the coadjoint. So you have this action, the coadjoint action on G star, and the orbits of this action are the symplectic leaves of G star. So you can describe the symplectic leaves of these manifolds as J minus 1 of the coadjoint orbits moved out by G. This is, I think, very, very cute. Okay. Okay, so let me introduce what happened in this contact world. So, and I want to start with one example to illustrate what is a Jacobi manifold. That is not like in the case of Poisson that everybody knows what is a Poisson manifold. Jacobi manifolds are not so well known. So I want to illustrate with one example that comes from the spheres on duals of Lie algebras. Okay, so you have a Lie algebra G. And you take a basis, so you can write, you have a basis EI, E1 up to En, let's say, and then you look at the constants, the structural constants. Okay, so this Lie algebra induces a linear Poisson structure on the dual, which is written as follows. So if you have that xi are the duals of this basis, dual of AEI, you can write, so this will be coordinates on G star, and then you can write down the Poisson by vector here as, so at the point x is just Cijk xk d dxi wedge d dxj. Okay, so it's called linear because obviously from this definition you have that if you put a t here, then it does like this. So if you put t here, then of course you get t outside. Okay. Well, okay, now let's put a scalar product on G. When you put a scalar product on G, then you can talk about the spheres on G star. Okay? So when G or G star has a scalar product, one can talk about the spheres. So these are the covectors of G star with so that the norm is 1. Okay? And then you ask the following question. Can I induce, like, can I restrict my bracket, my Poisson bracket of G star minus 0, let's say, to a bracket here on the spheres? And the answer is that, well, you can define a bracket, but it won't be Poisson. It will fail to satisfy Leibniz. Okay? So what you can do, actually what you do is the following. So you consider this projection, which goes from G star minus 0 to the sphere, that sends every covector to the covector divided by the norm, which I will denote by R of x. Okay? And then you define the bracket of two functions on this space by the following rule. Okay, so you define this bracket so that the pullback of this function to a function here, it satisfies that it's equal to 1 over R, where R is the norm, times R P star of F, R P star of G. This is the Poisson bracket on this space. Okay, so what happened is that, well, there is something that you have to check, right? You have to check that this thing here is actually projectable, right? So it doesn't depend. You have to check that if you put, if you evaluate this function at Tx for t positive number, then it coincides when you put only x. If you check that, then you know that this function is projectable, and then you define the bracket of this one as the, so if you prove that this coincides, then this is, I don't know, this is projectable. It means that it's the pullback of a function on S, on the sphere, and then you define this bracket as H. Okay? So there is only this thing that you have to check, that this is projectable and this is straightforward from the definition. I mean, you do just a very straightforward computation and you use that the Poisson bracket is linear, and that's all. Okay. So when you have this bracket, so okay, so here I can tell you something. So this is somehow I can now tell you what is a Jacobi manifold. So a Jacobi manifold P, it's a manifold endowed with a bracket, with a Lie bracket on the space of functions, which is, well, it will not satisfy Leibniz, but it is local. Local in the sense that if you take the bracket of two functions, then the support of this bracket is inside of the support of F intersected with the support of G. From this example, I mean, if you take P as the sphere and this bracket defined as I did, well, this satisfies these conditions of locality. Okay, and what it follows is that actually if you look at this projection, so you have this projection of G star minus 0 to the sphere. The two brackets that I have, this one and the one coming from the Poisson structure, are related by the formula that I get there. Okay? So you can think of this as a manifold M and this as another manifold P, Jacobi manifolds. This is a function P, and then you have this R, right? You have an R right there, which is the norm. So this would be a function on my M, and then you have this corollary definition, which is that that this P is a Jacobi map with conformal, in this case, this is R, right? With conformal factor A equal to R in this case, which means that A times alpha star of F, A times alpha star of G, it's equal to A times alpha star of the bracket. And here it's on P. This is on M, and here is on P. So the corollary is that for the sphere this happens, okay? For the sphere and the bracket, so the bracket of G star and S of G star, well, it's not a corollary, it's actually a definition of my bracket here, satisfies this condition. And the definition here is that what is a Jacobi map with conformal factor R? A Jacobi map with conformal factor R is a map that satisfies this condition. Okay. Okay, so the next question is the following. So now you know that for Poisson manifolds, the realizations are symplectic manifolds. Now you ask, okay, for Jacobi manifolds, what are the realizations? And the answer is that they are contact manifolds. So what is a contact manifold? A contact manifold, it's a manifold M endowed odd dimensional, endowed with a contact form. So this means that the differential wedge in times theta, it's never 0. And you can look at this condition, this is equivalent to say that if you look at the kernel of theta, this is a codimensional 1 distribution, okay? And you have that if you endow this with, and you look at the restriction of the theta to this space, this is actually a symplectic, it's symplectic. So this is a non-degenerate two form on this space, okay? So out of a contact manifold, I can produce a Jacobi structure. So I can produce a bracket on the space of functions on M. And then, well, how you define that? So as in the symplectic case, you have Hamiltonian functions here. They are defined as follows. Hamiltonian function, no, Hamiltonian vector. So if you take a function, then you define the Hamiltonian vector as follows. So this is the unique vector that satisfies two conditions, that when you apply theta to the vector, it's actually the function. And the second condition is one coming from the differential of theta, which says that d theta xf, and here. So this is a one form, right? This will be equal to minus the differential of f plus the Lie derivative of the real vector field applied to f times theta. The real vector field is just a vector field on the manifold which is transversal to H, okay, and satisfies some other conditions. So H is codimensional 1. The real vector field is the one that complements H. Okay, and then when you have these Hamiltonian vector fields, you define the bracket on the space of functions as follows. So you define f, the bracket of these two functions, as you take the Lie bracket of these Hamiltonian vector fields and you apply theta. Okay. Now, so as I was telling you, the realizations of Jacobi structures are contact manifolds. So in the sense that, well, in the sense that you think, so a realization of a Jacobi manifold by a contact manifold is just a map from my contact manifold to P, which is Jacobi with conformal factor, some function which is never 0. Okay, so going back to my example, let's see how we can construct a realization of my sphere. So I have my sphere, I have a Jacobi bracket. How can I construct a realization? A realization. Okay. So now, remember that you start with your Lie algebra G, and now you consider a Lie group, well, one Lie group that has Lie algebra G. So G, it's a Lie group with Lie algebra G. And remember that I end out G with a metric or a scalar product. Okay, so now this metric on G or G star, they are isomorphic. Now this metric, remember that, well, the Lie algebra is just the tangent of G at the unit. So whenever I have a metric here, I can induce a metric on the space on the tangent of G or the cotangent space of G, I will induce a metric which is left invariant. Okay, so how do I define it? So I take two vectors of G, let's say they are at the point G of G. What I do is that I left translate them to the unit. So so here I have this map which is given by left multiplication by G minus 1. So I left translate these vectors, and then I take the the scalar product there. So this is my definition. This will be a left invariant metric. Invariant metric. Okay, so as soon as I have a metric on the tangent or the cotangent space of G, I can talk about the sphere on this space, on the cotangent space of G, of the Lie group. Okay, so now I have this sphere on T star of G. T star of G, and actually another way to describe this space is that this space is actually trivializable, as T star of G is. T star of G is isomorphic to G times the dual of the Lie algebra. Okay, so I can also play this game here, and I have that this one is isomorphic to G times S of G star. And, well, I use the left trivialization. So if I have a covector here, what I do is, well, this goes to G times, and then I left translate this covector to a covector on the unit, okay? Because my metric is left invariant, this sends the sphere on the sphere. I don't have any problem. Okay, but the reason why I consider this space, seeing it as a submanifold of T star G, is that here I have a canonical one form, which is the Liouville one form. And actually, the Liouville one form restricted to the sphere will become contact. Okay, so you have this non-degeneracy condition when you restrict that form on the sphere. Okay, and so now I produced a contact manifold, which is this one. So this one, T star G, end up with this form, which is the restriction of the Liouville one form. I will describe it in a second. Restricted to S of T star G. And then using this trivialization, I can look at this form here. Okay, this contact form here is just, so when I look at this form here in this space, so I do the pull back, then this form is very cute. So this form applied at some point here, so at G times mu a covector, applied to well, the tangent of this, you decompose it as T of G times T of S, so two vectors. This one will be on T of G, and this one will be on T of S. This is just, you evaluate, so you left translate this one to the unit, right? This is a vector on, this will be a vector on G. So you left translated to the unit, and then you left translated to the unit, right? And then you apply mu. Remember that mu is a covector of norm 1. So it's mu L of G minus 1 of D of G. Great. So, okay, so let's see now how this space realizes my sphere. How this space, which is, well, realizes the sphere of G star. what happened is the following. And actually, this story that I will tell you follows in more generality. It's a construction that you have. So what happened is that you have an action of G on this sphere, which is just given by left translation. Because my metric is left invariant, then this action restricts is well defined. Okay? If you look at this action on this space, which is isomorphic, right? So here I define it as left translation, but if you look what happened with the action in the right-hand side, you see that actually G is only acting on this component by left multiplication. So the action is very simple. You act, so you take G here, and you act on H times mu, and this is just G times H, comma mu. Okay. And what happened here, the cool thing is that if you look at this action here, now that you already have the formula of theta, you can check that this form is invariant under this action. Okay? So let's see now. I want to be a bit more general, so I want to call this M. So you have an action of G on M, and then you have that the action preserves the form. So G preserves theta, which means that whenever I have this G and I look at the action, then this pullbacks theta to theta. And that's what we call, well, I want to call this a contact action. This is a general definition, okay? So you have a contact manifold, you have a Lie group acting, and you have this condition, then you call it a contact action. As soon as you have a contact action, you get like a moment map. Okay, so you get a moment map, which is a map from M to the dual of the Lie algebra of G. Okay, and this moment map is defined as follows. So J at x a point here, then what you get is a map from G to, so it's an element of G star, so this is a map from G to R. Okay, so let's see what it does to an element of G. And this is defined as theta of x applied to theta of M, where this is the infinitesimal generator of the action. Generator of the action. So this vector field is defined as follows. Theta M at some point x is just ddt of the exponential of t times psi. Applied, so this is an element of G, and then you apply to x, okay? Nice. So in our case, what happens is, you see that in our case, the Lie group is acting only on the left component, on G, by left multiplication. So if you look at the infinitesimal generator, it's the right invariant vector field induced by theta in the first component, and the second component is 0. Okay, so in our case, so theta, and my manifold here is G times S of G star. Theta, it's just, so it has two components. The component of G is just the theta of G, which is, this is the, and in the second component, it's 0, right? This is the right invariant vector field of theta. Okay, so hence, it's very easy to compute this j. Let's do one computation. Okay, so j at so you take a point on g times the sphere, so g times mu, and you apply it to this covector, this vector, right? This is an element of my Lie algebra. So this is only theta at this point applied to the right invariant vector field times 0. And by our definition of theta there, this is mu applied to left multiplication by g minus 1 of this vector. But because this is the left invariant vector field, the right invariant vector field associated to theta, this is right translation by g of theta, right? So what you get here is the adjoint of g applied to theta. And then, well, this is just the pullback of the coadjoint applied to mu evaluated at theta. Well, I will write the conclusion here. So j of g mu, it's equal to the coadjoint at g applied to mu. Nice. Okay, so proposition j, well, let's say in general, Bailin is Jacobi. It's a Jacobi map. Okay, so what we can conclude from here is that, coming back again to our example, we have this j times s g star. So this is saying that this is a realization of this Jacobi, of this as a Jacobi manifold. Okay, so in our example, coming back to our example, so we have this j here that goes to g star, and if the image of j does not intersect 0, which in our case it happens that it doesn't intersect 0, then remember that you have this other projection to the sphere, right? This is Jacobi, this is Jacobi. This is with conformal factor r, so this will be Jacobi. This is theta lives here. This will be Jacobi with conformal factor. So let's see what is this map. This map sends g times mu to the adjoint, the coadjoint of g applied to mu divided by the norm. Okay, so this is Jacobi with conformal factor. Let's call this map beta, so we remember. With conformal factor, with conformal factor, b equal to the pullback of the conformal factor of this one. So this is just b applied to g of mu. It's equal to the norm of the coadjoint action applied to mu. Okay. Okay, but now let's see from here. So now you have, whenever you have this contact action, you have this map, which you already know that it's a Jacobi. And then, well, here, this leads us again to this very natural question of what happened with the orbits of the, well, with the quotient space, okay? How can I relate the geometry in this side to the geometry of the quotient? Because the action is contact, then you have a Jacobi structure here. You can prove that you have a Jacobi structure here, but let's wish that it actually Poisson. So these are very related, okay? So if we assume that this manifold, that this quotient is Poisson, this quotient is Poisson, you see that this happens if and only if the vector field, well, this is a computation, but this happens if and only if the vector field is tangent to the orbits, okay? So if and only if the vector field of theta is tangent to the orbit. And in this case, assuming this, in this case, this will be an example of a contact dual pair, okay? This will be a contact dual pair. Actually, so from here, if you assume some conditions about J, you can, so you have these two Poisson manifolds, and if you assume some conditions, then actually this is in the work of Chen Chang and Zambon. You can describe the symplectic leaves of this space as J minus 1 of the coadjoint orbits modulo the action, which is nice. I mean, this is very well. It gives you a description of the geometry of this manifold. Okay, but what I'm telling you here, it's a more general result. It's a result that we have, and it's that if you assume some conditions, which I will tell you in a little bit, you have this correspondence between the natural foliations that you have on the Jacobi manifolds. Okay? Okay. Let's see again, let's go back to our example. I hope you like the example because it's the only one I have in the blackboard, I mean. I have more, but not here. Okay, so in our example, we have this G-act here. I have my form, and then, well, remember that you are only acting here, but left multiplication, so the quotient will be the sphere, right? And the projection will be projection to the second component. And, well, we are assuming, I deleted it. Okay, we are assuming that this is Poisson, so actually this is the restriction of the linear Poisson bivector. And this again will be, this is my, what was it? It's given by something like this. And this is again a dual pair. Okay, so let me tell you what it's a dual pair now. Now that you have these examples, a dual pair is just a contact dual pair. It's, well, between two Jacobi manifolds. It's a realization by a single contact manifold. Right? Here is alpha, my map, and this is the conformal factor A. and here the map is beta, and the conformal factor will be B. So these are Jacobi, so that the fibers are contact orthogonal. So the kernel, no, before that, so that the fibers are transversal to the kernel of H, to the kernel of theta. And again, when I look at the pullback of the functions of these two spaces here on M, they centralize each other. Okay? So what I want is that if I have F1 equal to A for F in the function in P1, and then I have F2 defined analogously. What I want is that they centralize each other here, right? These are functions on M. So this F1, they centralize each other. Okay, so if you spell out these conditions, this global condition, and you want to write this global condition in a like more finite condition, then you get the definition of contact dual pairs. So contact dual pair is like these two Jacobi maps, so that the fibers are transversal to the kernel of theta, plus these other conditions, which are like, if you take the Jacobi bracket of these two functions on M, this is 0. The second condition is that the Hamiltonian vector fields, the Hamiltonian vector field of A belongs to the kernel of beta, and the one of B belongs to the kernel of alpha. And the third condition is that the fibers are contact orthogonal. So kernel of T beta intersected with kernel of theta is contact orthogonal to this one. Okay, this comes from looking how can you spell out this condition about centralizing these algebras. And you defined full dual pairs. So a contact dual pair is full if alpha and beta are submersions. And actually what you get is that for full contact dual pairs defined like this, so that the fibers are connected. This implies that these F1 and F2 centralize each other. So actually this is an equivalent definition modulo some connectedness and this assumption of being submersions. Okay. Okay, so for example, if you think about contact dual pairs as Morita equivalence, then you should expect some result about the leaf spaces of the Jacobi manifolds, right? And what you get is the following. So let me tell you this. So if you have a Poisson manifold, this is foliated by symplectic manifolds. For Jacobi manifolds, they also have a natural foliation. It's just that it's a bit more complicated. The leaves are or contact or locally conformally symplectic, but you have a natural foliation there, right? And the result is that if you have this full contact dual pair, full contact dual pair with connected fibers, then the map that assigns a leaf of P1, right? So what you can do is that you look the inverse image. So you look at the inverse image. This lives in M, and then you push it with beta. This will be a leaf of P2. And they have the same type of geometry. So they are either contact or either locally conformally symplectic. And this is a correspondence. And actually, you have correspondence. And actually, you have more. You can relate the, let's say if this is contact, you can relate the contact forms of this one and this one on M. There is a formula. Also for locally conformally symplectic. Okay. So I have like 5 minutes, right? It's fine because I'm finishing. Okay, so coming back to our example. No, let me tell you some other example, which is not very example, but kind of, which are contact groupoids. Contact groupoids. Well, a contact groupoid, it's a Lie groupoid, G, over my manifold M. I will denote the source with alpha and the target with beta. It's a Lie groupoid endowed with a contact structure which is multiplicative with respect to some multiplicative function, okay? So this is multiplicative with respect to this function on G, which is multiplicative. It satisfies some, is natural somehow with the multiplication of G, okay? So whenever I have a contact groupoid, as in the case of symplectic groupoids, if you have a symplectic groupoid induces a Poisson structure on the base manifold. In the case of contact groupoids, they induced a Jacobi structure on the base manifold, okay? And what happened, the corollary is that contact groupoids are, well, a contact groupoid is a full contact dual pair, and the conformal factor for the source is 1, and the conformal factor for the target is minus C. Okay, in this case, this correspondence will be the identity. Okay? Okay, so we go back to our example. Spheres on the duals of Lie algebras. Remember that you have, so you have G with the algebra G. Then you take this one and a metric. Okay, so we had this map before, right? So remember that we have this realization. Beta, which is the adjoint, it's like the adjoint divided by the modulo 2s of G star. This is Jacobi. Okay, so let's assume now that the metric is G invariant. So, okay, so let's assume that the metric is G invariant. This, you can assume that, for example, when G is compact, okay? So here, because it's G invariant, so it means that it's invariant under the coadjoint action. This will be 1. But you get more. You get that, in fact, this manifold here, this thing here, is the action groupoid. So G times S of G star is an action groupoid. Is an action groupoid where the action of G on this manifold is given by the coadjoint action. So G times mu, it's equal to the coadjoint of G applied to mu. Okay? So what happened is that if you look at this action groupoid, the target will be actually beta, and the source will be the projection to the second component. Okay? So you get for free that this is a full contact dual pair, because it actually in this case is a contact groupoid. You can check that this multiplicative this form is multiplicative as well. Okay, that's all what I wanted to say.